Hello students, I hope you all are doing good. Today we are going to discuss NCERT exercise of chapter atoms. This is the disclaimer. Let's start by looking at what you will be able to do after this lecture. Our focus is on atoms, and by the end you will have a clear understanding of some key atomic models and how to apply atomic physics concepts. You would be able to understand the difference between Thomson's and Rutherford's atomic models. You will also be able to understand the limitations and key features of both models. Next, you will be able to apply Bohr's model and other key concepts in atomic physics. You will learn how to calculate these energy levels, use quantum numbers to describe electron positions, and solve numerical problems involving atomic structure and radiation. This will help you apply these concepts to real-world physics problem. Let's see the index of topics that we are going to cover today. There are total 9 NCERT exercise questions in chapter atoms. Now let's focus on what we will be doing today. In this lecture, we are going to go through all of these questions from 12.1 to 12.9. So this question asks here to choose the correct alternative from the clues given at the end of each statement. Okay, question presents a set of statements about the structure of atoms focusing on the differences between Thomson's and Rutherford's atomic models. Notice how each statement asks you to compare or contrast features like atomic size, electron stability, mass distribution, and where the positive charge is located in each model. These questions test your understanding of key concepts, what each atomic model proposed about the arrangement of electrons and positive charge. Secondly, how the model explain stability and mass distribution inside the atom, and which model predicts certain physical behaviors like whether electrons are in equilibrium or if the atom would collapse according to classical physics. So statement given are: first statement A, the size of atom in Thomson model is dash the atomic size in Rutherford model. Okay, and clues are given: much greater than, not different from, or much less than. B, in the ground state of dash electrons are in stable equilibrium wherein dash electrons always experience a net force. Okay, and options are Thomson's model, clues given are Thomson model or / Rutherford's model. C part, a classical atom based on dash is doomed to collapse. Okay, and clues are Thomson's model, Rutherford's model. D part, an atom has a nearly continuous mass distribution in a dash but has a highly non-uniform mass distribution in dash. Clues are Thomson's model, Rutherford's model. And E part is the positively charged part of the atom possesses most of the mass in dash, Rutherford model or both the models. Okay. So let's look at some key differences between Thomson's and Rutherford model of the atom. You have to choose the correct alternative for each statement and then we will discuss the answers. Pay attention to the clues at the end of each statement. They will help you to think about the properties of each model. Let's start with part A. Both Thomson's and Rutherford model describe atom as being about the same size, even though the internal structures are very different. This means that the overall diameter of the atom doesn't change much between the two models. Emphasize that the main difference is in how the positive charge and mass are distributed, not the size itself. Notice here that the correct answer is not different from. The size of the atom in Thomson's model is not different from the atomic size in Rutherford's model. This shows us that while the internal arrangement of particles changed, the estimated size of the atom remained similar in both models. Now let's look at part B. In Thomson's model, electrons are embedded in a sphere of positive charge and are in stable equilibrium. They don't move unless distributed. But in Rutherford's model, electron orbits the nucleus and always feel a net force pulling them towards the center. This is a key difference in how each model explains electron behavior. For part C, a classical atom based on Rutherford's model is doomed to collapse. That's because, according to classical physics, an electron moving in a circle should emit energy and spiral into the nucleus. This was a major problem with Rutherford's model and led to the development of new atomic theories. Now let's focus on part D. In Thomson's model, the atom's mass is spread out almost evenly like a pudding with raisins. So we say it has a nearly continuous mass distribution. In contrast, Rutherford's model showed that almost all the mass is concentrated in a tiny nucleus at the center, making the mass distribution highly non-uniform. This difference is crucial because it explains why most alpha particles pass straight through gold foil in Rutherford's experiment, but a few are deflected sharply. Finally, let's look at part E. In both Thomson's and Rutherford's model, the positively charged part of the atom holds most of the mass. In Thomson's model, the positive charge is spread throughout the atom, while in Rutherford's model, it's all packed into the nucleus. This means that regardless of the model, the positive component is always much heavier than the electrons. Now let's examine what this question is asking. It imagines repeating the famous alpha particle scattering experiment, but instead of using a gold foil, thin sheet of solid hydrogen is used. Solid hydrogen is possible at temperature below 14 Kelvin. Okay, notice how this is an application question. It tests your understanding of the alpha particle scattering experiment and the structure of atoms, especially the difference between hydrogen and gold atoms. Think about what would happen to alpha particles when they interact with hydrogen atoms compared to gold atoms. This problem checked your grasp of atomic structure, that is nuclear size, number of protons, the concept of nuclear charge, and how these affect the scattering of alpha particles. First, let's recall what happens in the original experiment. If we use solid hydrogen instead of gold, the alpha particles won't be scattered at large angles. This means we wouldn't see the dramatic deflections that Rutherford observed with gold foil. Why is this? It's because the mass of a hydrogen nucleus is much smaller than the mass of an alpha particle. Specifically, hydrogen has a mass of about 1.67 times 10 to the power minus 27 kilograms, while an alpha particle is about 6.64 times 10 raised to power minus 27 kilograms. So the incoming alpha particle is actually heavier than the hydrogen nucleus it hits. This difference in mass is important since the alpha particle is more massive than the hydrogen nucleus. It won't be deflected backwards. Instead, it will mostly keep moving forward with only small changes in direction. The lighter hydrogen nucleus just can't push the heavier alpha particle back. So to sum up, if we use the solid hydrogen in the alpha particle scattering experiment, we wouldn't see any alpha particles bouncing back. The key takeaway is that the mass and charge of the target nucleus plays a big role in how particles scatter. Let's see what this question is asking. NCERT exercise 12.3, it gives us two energy levels in an atom separated by 2.3 electron volts. The question wants to know the frequency of radiation emitted when the atom moves from higher energy level to the lower one. Notice how this is a classic example of energy transitions in atom, where energy is released as electromagnetic radiation. This problem tests your understanding of the relationship between the energy difference and frequency of emitted radiation. First, let's note the information given. The separation between the two energy levels is 2.3 electron volt. This value tells us how much energy is released when atom makes the transition. Here we write the energy difference as E equal to 2.3 electron volt. The symbol E stands for energy, and electron volt is a common unit of energy in atomic physics. However, for calculation, we usually need to convert this to joules, which is SI unit for energy. Now let's convert electron volts to joules. We use the conversion factor. 1 electron volt equals to 1.6 times 10 to the power minus 19 joules. Okay, so E is equal to 2.3 times 1.6 times 10 to the power minus 19. After multiplying, we get E equal to 3.68 times 10 to the power minus 19 joules. This is the energy released during the transition. Okay, next, frequency of the emitted radiation. We will use the symbol nu, which stands for frequency and is measured in hertz. The frequency tells us how many wave cycles are emitted per cycle. To solve this, let's recall the basic relationship between the energy of a photon and its frequency. The energy of the emitted radiation is directly related to its frequency. We'll use the formula E equal to h nu, where E is energy and h is Planck's constant and nu is the frequency. Okay, here h stands for Planck's constant, which is 6.62 times 10 to the power minus 34 joule seconds. This is the fundamental constant in physics that relates the energy of photon to its frequency. Now let's rearrange the formula to solve for frequency. We get nu equals E divided by h. This means that if we know the energy difference and Planck's constant, we can directly calculate the frequency of the emitted radiation. Let's plug in the numbers. First, we need to convert 2.3 electron volts to joules. 1 electron volt is 1.6 times 10 to the power minus 19 joules. So 2.3 electron volt is about 3.68 times 10 to the power minus 19 joules. Dividing this by Planck's constant, 6.62 times 10 to the power minus 34 gives us a frequency of about 5.55 times 10 to the power 14 hertz. This is in the visible or near visible range of the electromagnetic spectrum. So to summarize, the frequency of the radiation emitted during this atomic transition is approximately 5.6 times 10 to the power 14 hertz. This shows how even small energy differences at the atomic level corresponds to a very high frequencies of light. Let's see the question about the hydrogen atom ground state energy. The slide tells us ground state energy is minus 13.6 electron volts. This is the lowest possible energy the electron can have in hydrogen atom. The question asks for both the kinetic energy and potential energy of the electron in this state. This problem tests your understanding of how total energy, kinetic energy and potential energy are related in atomic physics, especially for the hydrogen atom. So first, let's note that the ground state energy of the hydrogen atom is equal to minus 13.6 electron volts. The negative sign means the electron is bound to the nucleus. It would take 13.6 electron volts of energy to remove it completely. This value minus 13.6 electron volt represents the total energy of the hydrogen atom in its ground state. Total energy here is the sum of electrons' kinetic energy and its potential energy due to the attraction of the nucleus. It's important to remember that in bound systems like atoms, total energy is negative. Now let's talk about kinetic energy. In the hydrogen atom, the kinetic energy of the electron is equal to the negative of the total energy. This means if the total energy is negative, the kinetic energy will be positive and of same magnitude. This is a result from solving the equation for hydrogen atom in quantum mechanics. So the kinetic energy equal to minus E, which is minus negative 13.6, which gives us positive 13.6 electron volts. This tells us the electron is moving with enough energy to balance the strong attraction from the nucleus, but not enough to escape. Notice how the kinetic energy is always a positive value. Next, let's find the potential energy. For the hydrogen atom, the potential energy is always twice the total energy. Calculating this potential energy, PE equal to 2 times E, so that 2 times minus 13.6, which equals minus 27.2 electron volts. The negative sign shows that electron is in a bound state. Let's see what this question is asking. A hydrogen atom in its lowest energy state, the ground level, absorbs a photon and jumps up to n equal to 4 energy level. You have to find the wavelength and frequency of the photon. Notice how this is an example of an excitation process where an atom absorbs energy and an electron moves to a higher energy level. This question tests your understanding of atomic energy level, photon absorption, and how to calculate the wavelength and frequency of the light involved in such transitions. So first let's identify the ground level. For hydrogen, the ground state means N1 equals 1. This N value is called the principal quantum number and it tells us which energy level the electron is in. So N1 equal to 1 is the lowest possible energy state for hydrogen. Now let's talk about the energy of this level. We will call it E1. The energy of any level in a hydrogen atom depends on its N value. The formula for energy of the nth level is E equal to minus 13.6 divided by n squared with the result in electron volts. This formula comes from the Bohr model of the atom. So let's substitute N1 equal to 1, okay, in the formula. So formula is E1 equal to minus 13.6 upon N1 square electron volt. This is NCERT equation 12.10. Okay, so by substituting N1 equal to 1, we got E1 equal to minus 13.6 upon 1 square, which gives minus 13.6 electron volts. Now let's focus on what happens during excitation. The atom is excited to higher energy level, specifically N2 equal to 4. Here N stands for principal quantum number, which tells us which energy level the electron is in. The higher the value of N, the higher the energy and farther the electron is from the nucleus. Next, let's define E2, which is the energy of the level the electron has moved to. E2 represents the energy of the hydrogen atom when the electron is in N2 equal to 4 state. We will need this value to calculate the energy difference between the initial and final states. Therefore, E2 equals minus 13.6 upon N2 square electron volt according to NCERT equation 12.10. Let's substitute N equal to N2 equal to 4 into the formula. So E2 equals to minus 13.6 divided by 4 square, which is 16, which gives us minus 0.85 electron volt. Okay, this means that when electron is in the 4th energy level, the energy is minus 13.6 upon 16 electron volts. Notice how the energy becomes less negative as n increases, showing the electron is less tightly bound. First, let's figure out how much energy the atom absorbs. The energy absorbed by the photon is equal to the difference between the final and initial energy levels of the atom. We can write this mathematically as E equal to E2 minus E1. Here E is the energy of the emitted photon. Energy of the photon. E2 is the energy of the higher level n equal to 4 and E1 is the energy of ground state, that is n equal to 1. All energies are measured in electron volts, which is a common unit for atomic energies. Now let's substitute the actual values for E1 and E2. For hydrogen, the energy of level n is given by En equal to minus 13.6 divided by n squared in electron volts. And E1 is minus 13.6 electron volt and E2 is minus 13.6 divided by 16, since 4 squared is 16. Plugging in these values, we get E equal to minus 13.6 upon 16 minus 13.6 upon 1. Notice that double negative here means we are really adding the absolute values. After calculating, we find the energy absorbed is 12.75 electron volt. This is the energy of the photon that was absorbed to move the electron from n equal to 1 to n equal to 4. Next, let's convert this energy from electron volts to joules. Since SI units are preferred for further calculations, we use the conversion factor. 1 electron volt equals to 1.6 times 10 to the power minus 19 joules. So we multiply 12.75 by 1.6 times 10 to the power minus 19. This gives E equal to 2.04 times 10 to the power minus 18 joules. Notice we have the photon's energy in joules, which we can use to find its wavelength and frequency in next steps. To start solving this, let's recall how the energy of a photon relates to its wavelength. The energy of a photon is connected to its wavelength by a specific formula. The formula for energy of a photon is E equal to hc upon lambda. Here E is the energy of the photon and lambda is the wavelength. Now let's break down what each symbol in the formula stands for. First, H stands for Planck's constant, which is a fundamental constant in physics. Its value is 6.6 times 10 to the power minus 34 joule seconds. Next, C is the speed of light in vacuum, which is 3 times 10 to the power 8 meter per second. This is the universal constant. Now let's rearrange our formula to solve for wavelength lambda. This means we will express lambda in terms of H, C and E. So after rearranging, we get lambda equals to hc divided by E. This tells us that the wavelength of the photon depends on Planck's constant, the speed of light and energy of the photon. Notice that as the energy increases, the wavelength gets shorter. Here we see the formula for wavelength. Lambda equals h times c divided by E. Now let's substitute the known values into our formula. We will use h equal to 6.6 times 10 to the power minus 34 joule seconds, c equal to 3 into 10 to the power 8 meter per second, and E equal to 2.04 multiplied by 10 to the power minus 18 joule, which is energy difference between the two levels. So after substituting, we get lambda equal to 6.6 times 10 to the power minus 34 times 3 multiplied by 10 to the power 8 divided by 2.04 multiplied by 10 to the power minus 18. This step shows the actual calculation. The result is lambda equals 9.7 times 10 to the power minus 8 meter, which is 97 nanometers. This wavelength is in the ultraviolet region of electromagnetic spectrum. Notice how a higher energy photon corresponds to a shorter wavelength. To solve for frequency, let's recall the relationship between the speed of light, wavelength and frequency. The frequency of a photon tells us how many wave cycles pass a point each second. The formula is frequency written as nu equals c divided by lambda. Here c is the speed of light and lambda is the wavelength. Now let's substitute our values into the formula. We have c as 3 times 10 to the power 8 meter per second and lambda as 9.7 times 10 to the power minus 8 meters. Notice that the wavelength is given in nanometers. So we have converted it to meters for consistency with SI units. After calculating, we find the frequency is approximately 3.1 times 10 to the power 15 Hz. To summarize, the photon that excites the hydrogen atom from ground state to n equal to 4 has the wavelength of 97 nanometers and a frequency of 3.1 times 10 to the power 15 Hz. Let's see what this question is asking. Part A asks us to use Bohr's model to calculate the speed of electron in a hydrogen atom for the first 3 energy levels, n equal to 1, 2 and 3. Part B asks us to calculate the orbital period, the time it takes for the electron to make one complete orbit or revolution for each of these levels. It tests your understanding of Bohr atomic model, specifically how electron speed and orbital period depend on principal quantum number n. You will need to recall and use the formulas from Bohr's theory for electron speed and orbital period in the hydrogen atom. We are calling the electron speed in the ground state V1 and N1 equals to 1. The charge of the electron is represented by E. The formula we are about to use relates the electron's speed to these variables. Here is the key equation from the NCERT textbook. V1 equals E squared upon 4 pi epsilon naught times mv1 r1. In this formula, E is the electron charge, epsilon naught is the permittivity of free space, m is the electron mass, v1 is the speed, and r1 is the radius of the orbit. This equation comes from balancing the electrostatic force and centripetal force acting on the electron. Now let's substitute the quantization condition from Bohr's model, which says that mv1 r1 equals n1h divided by 2 pi, where h is Planck's constant. Plugging in this into our previous equation, we get a new expression for v1. Notice how the quantum number n1 appears in the denominator, showing that the speed depends on which energy level the electron is in. Simplifying further, we see that v1 equals E squared divided by n1 times 2 epsilon naught h. For the ground state, n1 is 1, so the formula becomes v1 equals E squared divided by 2 epsilon naught h. This tells us that as n increases, the speed decreases, since n is in the denominator. We will use this formula to calculate the speed for n equal to 1, 2 and 3. First, let's write down the formula for the speed of electron in the first energy level, n equal to 1, according to Bohr's model. The speed v1 is given by v1 equal to E square upon 2 epsilon naught h. Now let's list out what each symbol in our formula stands for. This helps us keep track of physical meaning and units for each variable. First, E is the elementary charge, which is the charge of a single electron. Its value is 1.6 times 10 to the power minus 19 coulombs. Next, epsilon naught is the permittivity of free space. This constant tells us how electric fields behave in a vacuum, and it tells the value is 8.85 times 10 to the power minus 12 Newton inverse Coulomb square meter inverse square. Finally, H is the Planck's constant, which is a key value in quantum physics. It relates the energy of a photon to its frequency, and its value is 6.62 times 10 to the power minus 34 joule seconds. Let's substitute these values into our formula for V1. We have V1 equals to 1.6 times 10 to the power minus 19 squared divided by 2 times 8.85 times 10 to the power minus 12 times 6.62 multiplied by 10 to the power minus 34. After calculating, we find that V1 equals to 0.0218 times 10 to the power 8, which is 2.18 times 10 to the power 6 meter per second. This means the electron in the first energy level of hydrogen moves at about 2.18 million meters per second. Notice how fast this is compared to everyday speeds. Let's focus on second energy level, where n equals 2. Here we are setting up the formula to find the electron speed in this orbit. Notice that as n increases, the electron is farther from the nucleus and its speed changes. Formula for orbital speed in energy level n2 equal to 2 is given by v2 equal to E square upon n2 2 epsilon naught h. Now let's substitute the actual values for each constant into our formula. After plugging in the numbers and calculating, we find that the speed of electron in the n equal to 2 level is about 1.09 times 10 to the power 6 per second. Okay, so after putting all the values, V2 becomes equal to 1.6 multiplied by 10 to the power minus 19 squared upon 2 multiplied by 2 multiplied by 8.85 times 10 to the power minus 12 multiplied by 6.62 times 10 to the power minus 34. Okay, and N2 here is 2. Okay, so therefore the electron speed in the second energy level is 1.09 million meters per second. Now let's focus on the third energy level where n equals 3. We are going to write down the formula for the speed of electron in this level. Notice that as n increases, the electron is farther from the nucleus and its speed changes. Here is the formula for the speed of electron in the third orbit. V3 equals to E squared divided by N3 2 times epsilon naught times H. Now let's substitute the actual numerical values into the formula. We have E as 1.6 times 10 to the power minus 19 coulombs, epsilon naught as 8.85 times 10 to the power minus 12 farad per meter, and H as 6.62 times 10 to the power minus 34 joule seconds. After plugging in all the numbers and calculating, we find that the speed of the electron in the n equals 3 level is 7.72 times 10 to the power 5 meter per second. Okay, this is much slower than the lower energy levels, showing that as the electron moves to higher orbits, its speed decreases. Therefore, V3 equals 7.27 multiplied by 10 to the power 5 meter per second. This value is important because it shows the quantitative relationship between the energy level and electron speed. Hence, the speed of the electron in a hydrogen atom in n equal to 1, n equal to 2 and n equal to 3 is 2.18 times 10 to the power 6 meter per second, 1.09 times 10 to the power 6 meter per second and 7.27 times 10 to the power 5 meter per second respectively. Now let's define what we are looking for next, the orbital period. We will call T1 the orbital period when the electron is in the first energy level. That is when n1 equals 1. The orbital period is the time it takes for the electron to make one complete revolution around the nucleus. The orbital period is related to the orbital speed. Specifically, it's the time taken to travel the full circumference of the orbit at a given speed. Let's see the formula that connects these quantities. The formula for the orbital period is T1 equals to 2 pi R1 upon V1. Here T1 is the time period or orbital period, R1 is the radius of the orbit for n equal to 1 and V1 is the speed of the electron in that orbit. Let's clarify what each variables means. R1 equal to radius of the orbit of the electron when it is in level n1 equal to 1. To start, let's recall that radius of electron's orbit in the hydrogen atom depends on the energy level or the value of n. Here we are focusing on the radius when the electron is in the first energy level, which is n1 equal to 1. The formula for the radius of electron's orbit in Bohr model according to NCERT question 12.7 is R1 equal to n1 square h square epsilon naught divided by pi m e square. Here Planck's constant h is a fundamental constant in physics. Its value is 6.62 times 10 to the power minus 34 joule seconds. The charge on an electron equal is 1.6 times 10 to the power minus 19 coulombs. This is the basic unit of electric charge in atoms and it is always negative for electrons. Epsilon naught is permittivity of free space and its value is 8.85 times 10 to the power minus 12 Newton inverse coulomb squared meter inverse squared. The mass of an electron m is 9.151 times 10 to the power minus 31 kilograms. This is very small mass, but it's essential for calculating the motion of electrons in atoms. Here we see the formula for the orbital period T1 of the electron in the first energy level. The period T1 is the time it takes for the electron to complete one full orbit, and it's given by T1 equal to 2 pi R1 upon V1, where R1 is the radius of the orbit and V1 is the speed of the electron. Notice that we have substituted the expression for R1 from the Bohr model, which involves Planck's constant h, the permittivity of free space epsilon naught, the electron mass m and electron charge e. All these variables are in SI units. Let's substitute the actual values from this constant into our formula. This step is important because it allows us to calculate the numerical value for the orbital period. We will use the standard value for h, epsilon naught, m and e and plug them into the equation we just discussed. Here is the full substitution with numbers. We have T1 equals to 2 pi times 1 squared times 6.62 times 10 to the power minus 34 squared multiplied by 8.85 times 10 to the power minus 12 divided by this, all divided by 2.18 times 10 to the power 6 times pi multiplied by 9.1 times 10 to the power minus 31 multiplied by 1.6 times 10 to the power minus 19 squared. This looks complicated, but it's just plugging in the constants. Here we are reminded that speed of the electron in the first orbit V1 is 2.18 times 10 to the power 6 meter per second. This value comes from the Bohr model formula for electron speed. After calculating, we find that orbital period T1 is 1.527 times 10 to the power minus 16 seconds. This means the electron completes one full orbit around the nucleus in a tiny fraction of a second. Let's focus on the second energy level where n equals 2. Here we are interested in finding the orbital period, which is time it takes for the electron to complete one full revolution around the nucleus. The formula for the time period at level n2 equal to 2 is T2 equal to 2 pi R2 divided by V2. Here T2 is the orbital period, R2 is the radius of the orbit for n equal to 2 and V2 is the speed of electron in that orbit. The 2 pi R2 part gives the circumference of the orbit and dividing by the speed tells us how long it takes to go around once. Now let's clarify what each variable means. R2 stands for the radius of the electron orbit when n equals 2. In the Bohr's model, the radius increases as n squared. So the orbit gets much smaller, much larger as n increases. The formula for R2 is R2 equal to n2 squared times h squared times epsilon naught divided by pi times m times e squared. Okay, this is NCERT question 12.7. Here n2 is the principal quantum number, which is 2 in this case. Here we see the formula for the orbital time period T2 of the electron in the second energy level. The period T2 is the time it takes for the electron to complete one full orbit and it's given by T2 equal to 2 pi R2 upon V2, where R2 is the radius of the orbit and V2 is the speed of the electron at n equal to 2. Notice how we have substituted the expression of R2 from the Bohr's model, which depends on the quantum number n, Planck's constant h and permittivity of free space epsilon naught, the mass of the electron m and charge of the electron e. All variables are in SI units. And the formula for time period T2 becomes equal to 2 pi n2 square h square epsilon naught upon v2 pi m e square. Now let's substitute the known values for all the constant and variables into our formula. This step is important because it shows how we move from a general equation to a specific numerical answer. Here is the full substitution with numbers. We have 2 pi times 2 squared times Planck's constant squared, that is 6.62 times 10 to the power minus 34, and 8.85 times 10 to the power minus 12, all divided by product of electron speed, that is 1.09 multiplied by 10 to the power 6 at n equal to 2, multiplied by pi times 9.1 multiplied by 10 to the power minus 31, that is the electron mass, and multiply by square of electron charge, that is 1.6 multiplied by 10 to the power minus 19 square. Okay, this step by step substitution help us keep track of each value and ensure accuracy in our calculation. At this point we clarify that v2, the speed of electron in the second orbit, is 1.09 times 10 to the power 6 meter per second. It's important to slate the value of v2 explicitly, so we know exactly what number is being used in the calculation. After calculating, we find the orbital time period. T2 is 1.22 times 10 to the power minus 15 seconds. This means the electron completes one full orbit around the nucleus in a tiny fraction of a second. Let's focus on the third energy level, where n equals n3, where n3 equals to 3. We are going to write an expression for the orbital period of the electron in this level. Here is the formula for the orbital period in the third level. T3 equal to 2 pi r3 divided by v3. In this equation, T3 is the time period, r3 is the radius of the third orbit, and v3 is the speed of electron in that orbit. Let's clarify what each variable means. So r3 stands for the radius of electron's orbit, where n equals to 3. In the Bohr model, the radius increases as n squared. So the third orbit is much larger than the first. Now let's look at the formula. R3 equal to n3 squared times h square times epsilon naught divided by pi times m times e squared. Here n3 is the principal quantum number. Now let's focus on the formula for the orbital time period T3 in the third energy level. The time period T3 is the time it takes for the electron to complete one revolution in the n equal to 3 level. The formula shown, T3 equal to 2 pi 3 upon V3, where R3 is the radius of third orbit and V3 is the speed of electron in that orbit. Notice how we have substituted expression for R3 in terms of n, Planck's constant h, and permittivity of free space epsilon naught, the electron mass m and electron charge e. So T3 becomes 2 pi n3 squared h squared epsilon naught upon V3 pi m e square. Next, we are going to substitute the known values for all the constants and variable into our formula. Here we plug in all the numbers into our formula for T3. So T3 becomes equal to 2 pi multiplied by 3 squared multiplied by 6.62 times 10 to the power minus 34 square multiplied by 8.85 times 10 to the power minus 12, all divided by 7.27 times 10 to the power 5 multiplied by pi multiplied by 9.1 times 10 to the power minus 31 multiplied by 1.6 times 10 to the power minus 19 square. Okay, so at this point it's important to clarify that V3, the speed of electron in the third orbit, is 7.27 times 10 to the power 5 meter per second. This value comes from earlier calculation using the Bohr model formula for electron speed. After calculating, we find that the orbital period for the n equal to 3 level is 4.2 times 10 to the power minus 15 seconds. This is the time it takes for electron to make one complete revolution around the nucleus in the third orbit. Notice how the period increases as the energy level increases, since the electron is farther from the nucleus and moving more slow. To summarize, the orbital periods for the first three energy levels are 1.52 times 10 to the power minus 16 seconds, 1.22 times 10 to the power minus 15 seconds, and 4.12 times 10 to the power minus 15 seconds, respectively, for n equal to 1, n equal to 2, and n equal to 3. Let's examine a question about the structure of hydrogen atom, specifically the size of electron's orbit. This question gives the radius of the innermost electron orbit n equal to 1 as 5.3 times 10 to the power minus 11 meters and asks for the radius of n equal to 2 and n equal to 3 orbits. This type of problem tests your understanding of the Bohr model of atoms, where electrons move in fixed orbits around the nucleus. Notice how the radius of each orbit depends on the principal quantum number n. In the Bohr model, the formula for the radius is Rn equal to n square r1, where r1 is the radius of the first orbit. First, let's note the radius of the innermost orbit in a hydrogen atom is called Bohr's radius. It's given as r1 equals to 5.3 times 10 to the power minus 11 meters. Remember, this is a very small distance, showing just how tiny atoms are. Let's see how we can find the radius for any orbit, not just the first one. In the Bohr model, the radius of the nth orbit depends on the principal quantum number n. This formula is Rn equals to n square times r1. Here Rn is the radius of nth orbit, n is the orbit number, and r1 is the Bohr's radius. Notice that as n increases, the radius increases by the square of n. So higher orbits are much larger. Let's apply this formula for the second orbit, where n equals to 2. We will call this radius r2. So r2 equals to n square times r1. For n equals to 2, that means r2 equals to 2 squared times r1. This step sets up to the substitute the actual values and calculate the radius. So now let's substitute the numbers. R2 equals to 2 squared, which is 4 times 5.3 times 10 to the power minus 11 meters. Multiplying this gives us the radius of the second orbit. So after calculating, we find R2 equals to 2.12 times 10 to the power minus 10 meters. This is the radius of the second orbit in the hydrogen atom. Notice how much larger it is compared to the first orbit. This shows how quickly the size of the atom increases as electrons move to higher energy levels. Now let's focus on n equal to 3 orbit. We will write an expression for the radius of this third orbit, which we call r3. So the formula for the radius of the nth orbit is Rn equal to n square times r1, where n is the orbit number and r1 is the radius of the first orbit, that is Bohr's radius, which is r1 equal to 5.3 times 10 to the power minus 11 meters. Let's substitute n equal to 3 into our formula. So r3 equals 3 square times 5.3 times 10 to the power minus 11. That means we are multiplying r by the radius of first orbit. After calculating, we find that r3 equals 4.77 times 10 to the power minus 10 meters. Notice how bigger this is compared to first orbit. Emphasize that each time n increases, the radius increases by n squared, not just linearly. To summarize, the radius for the n equal to 2 and n equal to 3 orbits are 2.12 times 10 to the power minus 10 meters and 4.77 times 10 to the power minus 10 meters respectively. Let's have a look at the question. An electron beam with energy 12.5 electron volt used to bombard hydrogen gas at room temperature. This question asks what series of wavelength will be emitted. Notice how this is a classic atomic physics problem about the electron excitation and emission in hydrogen atoms. This question tests your understanding of energy levels in hydrogen atoms, how electrons can be excited to higher energy levels, and how they emit photons as they return to lower energy states. You have to recall the concept of quantized energy levels and how transitions between these levels produce specific wavelengths that are called spectral lines. First, let's note the energy of the electron beam. It's 12.5 electron volts, or remember 1 electron volt is amount of energy gained by electron when it's accelerated through a potential difference of 1 volt. This energy will be transferred to the hydrogen atom during the collision. Next, recall that ground state energy of hydrogen atom is minus 13.6 electron volt. This negative sign means the electron is bound to the nucleus. It would take 13.6 electron volt to remove it completely. When the hydrogen atom absorbs energy from the electron beam, its energy increases. So we add the 12.5 electron volt from the beam to the ground state energy. Minus 13.6 plus 12.5 gives us minus 1.1 electron volt. Now let's recall the formula for the energy in the electron in nth orbit of hydrogen, equals to minus 13.6 divided by n squared with energy in electron volt. Here E is the energy of the level, n is the principal quantum number, and 13.6 is the ground state energy magnitude. Let's write out the formula, equal to minus 13.6 upon n square electron volt. This equation from the Bohr's model and is found in your NCERT textbook as equation 12.10. Notice how as n increases, the energy becomes less negative, meaning the electron is less tightly bound. Now let's try n equal to 3. We will substitute n equal to 3 into our formula to see what energy level that corresponds to. So plugging in n equal to 3, we get E equal to minus 13.6 divided by 3 square, that is 9, which equals minus 1.5 electron volt. This is close to minus 1.1 electron volt we found earlier, but not exactly the same. This suggests that electron is excited to just above the n equal to 3 level, but not quite to n equal to 4. Now let's analyze the energy levels involved. The calculated energy here is negative 1.5 electron volt, which is close to the energy of a hydrogen atom when its electron is in n equal to 3 energy levels. The n value refers to the principal quantum number, which tells us which energy level the electron is in. So after being hit by the electron beam, some hydrogen electrons are excited up to the n equal to 3 level. As these excited electrons return to the lower energy states, they can drop directly from n equal to 3 to n equal to 1. When this happens, the atom emits a photon with a specific wavelength. This direct transition from n equal to 3 to n equal to 1 produces a line in the Lyman series, which is a set of ultraviolet spectral lines unique to hydrogen. The Lyman series always involves electron falling to the n equal to 1 level. To find the exact wavelengths, we use the formula for the Lyman series, where the final energy level NF is 1. This formula relates the wavelength of the emitted light to the initial and final energy levels of the electrons. Formula for Lyman series is 1 upon lambda IF equal to 1 upon lambda I1 equals RH times 1 divided by 1 squared minus 1 divided by Ni squared. Now let's introduce the formula that helps us calculate the wavelength of light emitted when an electron transitions between energy levels in a hydrogen atom. This formula is 1 divided by lambda I1 equals to RH times 1 divided by 1 squared minus 1 divided by Ni squared. This equation is known as Rydberg's formula for hydrogen spectral line, especially for Balmer series. Let's clarify what each part of this formula means. Here RH for the Rydberg's constant, which has a value of 1.097 times 10 to the power 7 per meter. Lambda IF represents the wavelength of the radiation emitted when an electron transitions from a higher energy level to the ground state, first energy level. Now let's focus on the case where the electron excites the hydrogen atom to the n equal to 3 energy level. We are going to calculate the wavelength of the light emitted when the atom transitions from n equal to 3 down to n equal to 1, which is the ground state. This is an example of electron transition in the hydrogen atom. So here we use the Rydberg's formula to find the wavelength. So generalized formula is 1 upon lambda IF equals to RH times 1 upon NF squared minus 1 upon NI squared, where R is the Rydberg constant. For this transition, N1 is 1 and N2 is 3. Plugging in these values help us set up the calculation. And the equation becomes 1 upon lambda 31. That means wavelength of light emitted when electron is transitioned from n equal to 3 to n equal to 1 equal to 1.097 multiplied by 10 to the power 7, which is Rydberg constant, and multiplied by 1 upon 1 squared minus 1 upon 3 squared. Let's simplify the expression inside the parenthesis. 1 minus 1 upon 9 gives us 8 by 9. So the equation becomes 1 upon lambda 31 equals to 1.097 multiplied by 10 to the power 7 times 8 by 9. This step shows how the difference in energy levels affects the wavelength produced. Now we solve for lambda, the wavelength. Rearranging the equation, we get lambda 31 equals to 9 divided by 8 times 1.097 multiplied by 10 to the power 7. After calculating, we find that wavelength for this transition is about 102.55 nanometers. This value is in the ultraviolet region of electromagnetic spectrum. Let's focus on one possible transition when an electron jumps from the second energy level n equals to 2 down to first energy level n equals to 1. This is called the transition from n initial equals to 2 to n final equals to 1. The wavelength of the emitted radiation for this transition can be calculated using the Rydberg's formula, which relates the energy level of hydrogen to the wavelength of light emitted. Here is the Rydberg formula for hydrogen, 1 divided by lambda 21 for particular transition from n equal to 2 to n equal to 1. Okay, so lambda 1 upon lambda 21 equals 1.097 multiplied by 10 to the power 7 multiplied by difference between 1 over 1 squared minus 1 over 2 squared. Lambda 21 is the wavelength for the transition from level 2 to level 1. The constant 1.097 times 10 to the power 7 meter per meter is called the Rydberg's constant and it's specific to hydrogen. Now let's simplify the expression inside the parenthesis. 1 minus 1/4 equals to 3/4. So the equation becomes 1 divided by lambda 21 equals 1.097 times 10 to the power 7 meters times 3 by 4. To find the lambda itself, we arrange the equation. Lambda 21 equals 4 divided by 1.097 times 10 to the power 7 times 3. This step is just algebra solving for lambda. After plugging in the numbers and calculating, we find that lambda 21 equals 1 to 1.54 nanometers. This is in the ultraviolet region of the electromagnetic spectrum. It's important to note that this specific wavelength is characteristic of the Lyman series in hydrogen, which involves transition down to first energy level. Now let's focus on what happens when an electron in hydrogen drops from third energy level, that is n initial equals to 3, to the second energy level n final equals to 2. This type of transition produces light in the Balmer series, which is the set of visible lines in the hydrogen spectrum. The Balmer series always involves electrons ending at n equals to 2, so keep that in mind as we proceed. Now to find the wavelength of the emitted light, we use a formula called Rydberg's formula. This formula relates the wavelength of light to the initial and final energy levels of the electron. We will plug in our values for n initial and n final in the next step. So wavelength of emitted radiation is given by 1 upon lambda 32 equals to 1.097 times 10 to the power 7 times 1 divided by 2 squared minus 1 divided by 3 squared. Let's simplify the calculation. 1 over lambda 32 equals 1.097 times 10 to the power 7 times the difference between 1 over 4 and 1 over 9. This gives us 1.097 times 10 to the power 7 multiplied by 5 over 36. This step shows how the energy difference between the two energy levels determine the wavelength of the emitted light. Now let's focus on the calculation for wavelength when an electron transitions from the third to the second energy level, which is called Balmer series. The formula shown here is lambda 32 equals to 36 divided by 5 times 1.097 times 10 to the power 7. Here lambda 32 is the wavelength for the transition from level 3 to 2 and 1.097 times 10 to the power 7 per meter is the Rydberg constant. After calculating, we find that lambda 32 equals 656.33 nanometers. This value is important because it falls within the visible spectrum. Now let's summarize the result for the Lyman series. In this case, two wavelengths are emitted, 100 0.5 nanometers and 121.5 nanometers. The Lyman series involved transition where electron falls to the first energy levels, and these wavelengths are in the ultraviolet region, which is not visible to the human eye. Finally, in the Balmer series, we see that only one wavelength, 656.33 nanometers, is emitted in this scenario. This is the same value we calculated earlier. Now let's see the question about the Bohr model and how it applies to planetary motion. The question asks us to find the quantum number n that would describe the Earth's orbit around the Sun using the Bohr model's idea. Notice how the problem gives us the Earth's orbital radius 1.5 times 10 to the power 11 meters, speed 3 into 10 to the power 4 meter per second, and mass 6 into 10 to the power 24 kilograms. Okay, this is an example of applying atomic physics concept like quantized angular momentum to a real world large scale system. Let's start by listing out what information is given in the problem. First, we have the radius of Earth's orbit around the Sun, which is 1.5 times 10 to the power 11 meters. Remember, the radius is the distance from the center of the Sun to the center of the Earth as it moves in its path. Next, the Earth's orbital speed is given as 3 times 10 to the power 4 meter per second. This means the Earth travels 30,000 meters every second as it moves around the Sun. Finally, the mass of the Earth is 6 times 10 to the power 24 kilograms. According to Bohr model, angular momentum is not just any value, it is quantized, meaning it can only take on specific allowed values. This is a key idea in the quantum physics. Here is the quantization condition for Bohr model. MV equal to NH by 2 pi according to NCERT equation 12.5. In this formula, m is the mass of object, v is its speed, r is the radius of its orbit, n is the quantum number, and h is Planck's constant. Let's clarify what each symbol in the equation stands for. H is Planck's constant, which is fundamental constant in the quantum mechanics. Its value is 6.62 times 10 to the power minus 34 joule second. N is the quantum number. This is what we are trying to find. It tells us which allowed orbit Earth would be in according to Bohr's model. Now let's rearrange the equation to solve for n. So after rearranging, we get n equal to mvr 2 pi upon h. This formula lets us plug in the Earth's mass, speed, orbital radius, and Planck's constant to calculate the quantum number. Here is the formula we will use, n equal to mvr 2 pi divided by h. This formula comes from Bohr's quantization of angular momentum, which says that only certain orbits are allowed. Now let's substitute the values given in the question into our formula. We will use m equal to 6 times 10 to the power 24 kilograms, v equal to 3 times 10 to the power 4 meter per second, r equal to 1.5 times 10 to the power 11 meters, and h equal to 6.62 times 10 to the power minus 34 joule seconds. So after plugging in the values, we get n equals to 2 pi times 6 times 10 to the power 24 times 3 times 3 10 to the power 4 times 1.5 times 10 to the power 11, all divided by 6.62 times 3.10 to the power minus 34. When we calculate this, we find n equals to 25.61 times 10 to the power 73, which we can round off to 2.6 times 10 to the power 74, which is an incredibly large quantum number, showing just how different atomic and planetary scales are. So the quantum number that characterizes the Earth's revolution around the Sun is approximately 2.6 times 10 to the power 10 to the power 74. So this is all about today's lecture of NCERT exercise of chapter Atoms. I hope you enjoyed the session and understood it well. Thank you for your attention.